When people say Einstein was wrong, what they usually mean is not that general relativity failed. They mean that the universe turned out to be more complicated than Einstein in 1915, and more surprising than even he was willing to accept in 1917. But if I zoom out and ask a cleaner question, the one I care about as a cosmologist, it becomes this. Does Einstein's core idea about gravity still describe the real universe, from black holes to the expansion of space to the largest structures we can map? And the answer so far is yes. Not because we admire Einstein, but because the universe keeps passing his tests, even in places where we would have expected cracks. Einstein's key move was to stop thinking of gravity as a force that reaches across space and to treat it as geometry. Matter and energy tell spacetime how to curve, and curved spacetime tells matter how to move. That sounds abstract, but it becomes concrete the moment you realize that how to move includes how clocks tick, how light travels, and how distances behave. In general relativity, a planet does not feel a mysterious pull from the sun. It follows the straightest possible path in a curved geometry. And straightest here is not a metaphor. It is a precise thing called a geodesic, the closest analog to a straight line that exists in curved spacetime. The first big win was Mercury. Its orbit precesses. Newtonian gravity predicts most of that precession because other planets tug on Mercury. But there was a leftover amount that stubbornly refused to go away. General relativity predicts exactly that leftover. This was not a flexible fit. It was a sharp calculation. Then came light bending. If spacetime is curved, light should not travel in Euclidean straight lines near massive objects. During solar eclipses, starlight passing near the sun appears slightly shifted. That effect is small but measurable, and it matches relativity. Then there is gravitational redshift. Light climbing out of a gravitational well loses energy and shifts to longer wavelengths. We measure that on Earth and in space. And there is time dilation. Clocks at different gravitational potentials tick at different rates. That is not just a laboratory curiosity. GPS would drift by kilometers per day if we did not correct for relativity, both special and general. Those are strong tests, but they are still weak field tests. The deeper question is whether Einstein's picture survives in the strongest gravity we can find. That takes us to neutron stars and black holes. Neutron stars pack more mass than the sun into a sphere roughly the size of a city. Their gravity is intense. They also spin fast. Some emit lighthouse beams, and we see them as pulsars, ticking with incredible regularity. In certain binary systems, pulsars orbit another star, sometimes another pulsar. Their orbital periods change over time. General relativity says they should lose energy by emitting gravitational waves. The orbit should shrink and the period should decrease in a very specific way. We have measured that in multiple systems. It matches the relativistic prediction with high precision. That is one of the cleanest confirmations that gravity is not only curvature, but that curvature can ripple and carry energy away. And then we detected those ripples directly. LIGO and Virgo measured gravitational waves from merging black holes and neutron stars. The waveforms are not arbitrary. They encode the masses, spins, and the dynamics of the merger. General relativity predicts the inspiral, the merger, and the ring down in a way that can be compared to data. The match is striking. We also have images of black holes, or more precisely, images of their shadows against glowing accretion flows from the Event Horizon Telescope. The size and shape of those shadows are consistent with the black hole solutions of general relativity within current uncertainties. None of this proves relativity is the final theory. But it shows something important. Einstein's framework is not a fragile approximation that only works in the solar system. It works where gravity is brutal. Now let me turn to the part that people often misunderstand. Einstein introduced what we now call the cosmological constant. He did it because at the time he believed the universe should be static. His field equations naturally allow a dynamic universe that expands or contracts. He did not like that. So he added a term that acts like a uniform energy density of space itself, producing a repulsive effect that can balance gravity on cosmic scales. Later, when expansion was observed, he regretted adding it, at least according to the famous story. But the twist is that the cosmological constant came back, not as a patch to force a static universe, but as a simple way to describe something we actually observe: accelerated expansion. To understand why this matters, I need to be clear about what expansion of the universe means. It does not mean galaxies are flying through space away from a central point. It means the distances between galaxies, on average, grow because the metric that measures distance changes with time. Space expands. The evidence starts with Hubble's observation that distant galaxies are redshifted, and the redshift increases with distance. In an expanding universe, light gets stretched as it travels through expanding space, increasing its wavelength. That is the cosmological redshift. It is not the same as a simple Doppler shift from motion through space, though they coincide at low redshift. The expansion is described by a scale factor, and its rate is the Hubble parameter, which changes over cosmic time. General relativity is what gives us the equations that connect the expansion rate to the contents of the universe. When we assume the universe is homogeneous and isotropic on large scales, we use a space-time geometry called the FLRW metric. Plug that into Einstein's equations and you get the Friedmann equations. They tell you how the expansion evolves depending on matter, radiation, curvature, and any vacuum-like energy, such as a cosmological constant. This is where Einstein is still right in a very practical sense. The entire standard model of cosmology, what we call lambda CDM, is built by taking general relativity seriously on cosmic scales and then adding two dominant ingredients we do not fully understand: cold dark matter and dark energy, often modeled as lambda, the cosmological constant. Let me talk about dark matter first, because it is a case where people sometimes claim Einstein failed. What we actually see is this: galaxies rotate too fast in their outer parts if you only count the gravity from visible stars and gas. Galaxy clusters have too much gravitational pull compared to what their luminous matter can provide. Hot gas in clusters stays bound at temperatures that would otherwise let it escape. Gravitational lensing, the bending of background light by foreground mass, maps out mass distributions that are larger and more extended than the visible matter. On the largest scales, the pattern of galaxies in surveys, the cosmic web, and the way structure grows over time all point to a dominant matter component that does not emit or absorb light. These are not one-off anomalies. They are multiple, independent lines of evidence. And crucially, the lensing evidence is geometric. It depends on how space-time is curved by mass energy. When we map lensing in clusters, we infer the gravitational potential directly. The famous bullet cluster is often discussed because the hot X-ray gas, which contains most of the normal matter, is spatially separated from the lensing mass peaks, which align more with the collisionless galaxies. That separation is hard to explain if gravity is only modified and there is no extra mass component, though modified gravity ideas exist and are actively tested. The mainstream view is that dark matter is real matter, not a tweak to Einstein's equations, because it fits not only galaxy dynamics, but also lensing, cluster physics, and the early universe evidence from the cosmic microwave background. The cosmic microwave background, the CMB, is one of the strongest reasons I say Einstein is still right. The CMB is relic radiation from when the universe became transparent about 380,000 years after the Big Bang. Before that, photons were trapped in a plasma of electrons and nuclei. When electrons combined with nuclei to form neutral atoms, photons decoupled and have been traveling ever since, cooling as the universe expands. The CMB is almost uniform, but it has tiny temperature fluctuations at the level of tens of microkelvin. Those fluctuations are a snapshot of early density variations. Their angular pattern, measured exquisitely by missions like WMAP and Planck, contains acoustic peaks that depend on the geometry of the universe and its contents. When we fit those peaks with a model, general relativity plus a mix of normal matter, dark matter, radiation, and dark energy gives a remarkably consistent picture. It tells us the universe is close to spatially flat. It tells us the baryon density. It tells us the dark matter density. It tells us the age of the universe. And it tells us that structure formation needs dark matter because normal matter was coupled to radiation early on and could not start clumping efficiently until after recombination. Dark matter, being collisionless and not coupled to photons, could start clumping earlier, seeding the gravitational wells into which normal matter later fell. That is how you get galaxies in clusters in the time available. So where does dark energy enter? And why does it connect to Einstein? In the late 1990s, observations of Type 1a supernovae showed that distant supernovae were dimmer than expected in a decelerating universe. Type 1a supernovae are useful because they have a relatively uniform intrinsic brightness after calibration, so they act as standardizable candles. By comparing their observed brightness to their redshift, we infer the expansion history. The result was that the expansion has been accelerating for the last several billion years. That was shocking because gravity from matter should slow expansion down. In general relativity, to accelerate expansion, you need a component with sufficiently negative pressure. A cosmological constant does exactly that. It has constant energy density as space expands, and its pressure is negative in a way that drives accelerated expansion. This is where I think the phrase "Einstein was wrong" misses the point. Einstein's equations already allowed this behavior. The cosmological constant is not a violation of general relativity. It is a term consistent with the symmetries of spacetime. In fact, if you write down the most general form of the field equations respecting energy momentum conservation and covariance, the cosmological constant naturally appears. The real problem is not that relativity cannot handle dark energy. The problem is that we do not know what dark energy is physically. If it is truly a cosmological constant, it might be vacuum energy, an energy of empty space. But when we try to estimate vacuum energy from quantum field theory in a naive way, we get an answer that is wildly larger than the observed value. That mismatch is the cosmological constant problem. It is not a small discrepancy. It is one of the biggest gaps between theory and observation in all of physics. We can test whether dark energy behaves like a cosmological constant by measuring its equation of state parameter, usually called W, the ratio of pressure to energy density. For a pure cosmological constant, W equals -1 exactly, and it does not change with time. Observations so far are consistent with W being very close to -1, but the error bars still allow small deviations and mild evolution. We use multiple probes to constrain this. Supernovae measure distances. Baryon acoustic oscillations give a standard ruler imprinted in the distribution of galaxies, originating from the same early universe sound waves that made the CMB peaks. Weak gravitational lensing measures how large-scale structure distorts background galaxy shapes. Galaxy clustering and redshift space distortions measure growth of structure, which depends on how gravity works and how expansion competes with collapse. Put together, these probes increasingly support the lambda CDM framework. General relativity plus cold dark matter plus a dark energy component consistent with a cosmological constant. Now, there is a modern tension that keeps cosmologists honest. The Hubble constant, the current expansion rate, is measured in two broad ways. One uses the early universe, mainly the CMB, and a model to infer H0. The other uses the late universe, building a distance ladder from parallax to Cepheids to supernovae. or using other distance indicators.